Okay. Good morning. I'm about to start. Let me do the screen sharing thing. Good. So for those of you who are not here and watching on recording, I would like to see all your assignment marks by tonight, and they should include a breakdown for each question. I got some emails that just said 94, so I do need to know the breakdown for each question. So
Quick
Michael has,
question then. If we have sent it without a breakdown, do we resend it?
yeah, why not?
Okay.
Did you do that?
Yes, and someone else in the chat asked it too.
Yeah, because I'm going to have to enter marks for each question. So I'll try to process the marks tonight. Sorry, Friday night, and you should see them by Saturday, when I will also be busy working on assignment 3. Oh God. Okay. So today will be a bit of a lightweight lecture because I am, for one thing, I'm very sleepy. By Thursday, I get quite exhausted. So we're going to do a topic of great interest. It's called learning automata. So here the idea is you have an automaton and you don't know what it is. And by automaton, I definitely mean DFA here. Deterministic, finite automaton, no omega stuff. So there is an interesting theory about learning omega automata as well. So in learning automata, what you're given is a black box, which is the automaton. You don't get to look inside it and see the states and transitions and stuff, but you get to feed it letters and see how it reacts. And so then by feeding it enough letters, you find out, it's accepted this word, or it's accepted that word, or it's not accepted this word. And then the question is, can I learn the automaton just by doing these experiments, learn what it is? And people investigated this in the 50s and 60s, I think 60s. And Tom Gold basically showed that this was very difficult in the computational complexity sense of difficult. And basically people said, okay, we can't really do this efficiently. Until in 1987, Dana Angluin came up with a polynomial time algorithm, but she had a different model. And that's the model I'm going to use to explain how to learn an automaton from examples. So what we normally are doing is we are given an automaton and we're asked questions about it, like what does it accept, what does it reject, what's the regular expression corresponding to this, can you minimize it, etc. Is it equivalent to that automaton? In all of these, we have the explicit description and we're asked questions about the language. But here we don't have the automaton, we have the language, or at least samples from the language, not even the whole language. And somehow we have to guess the automaton. This looks difficult. So it was quite a surprise when Dana Angluin, so let me write her name, Dana Angluin, wrote a fantastic paper in 1987 called Learning an Automaton from Queries and Counterexamples. And here is her model. So she assumed that there was a teacher which is called the minimally adequate teacher. I hope I'm a minimally adequate teacher. So here is how the model works. you can ask the teacher, is W in L? Okay, so right off the bat, we lay down some ground rules. It's always regular languages. If you want to learn more complex languages, basically forget it. You're not going to be able to. So it's regular languages. Okay. And the thing we're trying to learn is a DFA. If you want to learn an NFA, forget it. That's going to be very hard. All right. So you can ask, is W in L? And the teacher will answer yes, no. So she has to tell you the correct answer. Okay, so you start getting some examples, not just positive examples, but also negative examples. So if you ask, is ABA in the language, and she says no, you know something now. And then after collecting some information, you propose an answer. So teacher says yes, in which case you're very happy, or no, and here is a counter example. So what is a counter example? A word in L that your machine rejects. So you proposed a machine, right? So your proposed machine rejects when it should be accepting, or a word not in L, which your machine accepts. Incorrectly accepts. So the teacher gives you one counterexample, and that counterexample may be either one of these. It's the teacher's choice, not yours. And the theorem Dana Angevin proved with polynomially many queries. In what? I'll tell you that in a minute. I always hate it when people say it's polynomial time, and I say, yeah, in what parameter? So I'll tell you the parameter in a minute. But with polynomially many queries, you are guaranteed guaranteed to learn the correct minimal DFA for L. Note, we've already proved there's a unique minimal DFA. So you will learn that one. So it doesn't matter if the teacher has some more complex non-minimized version of the automaton. You're not going to learn that. How can you possibly know that? But you will learn the correct minimized version, which is what you want. You want to be able to recognize L. Okay. So I'm not going to actually prove this theorem. I'm just going to proceed by way of example. So I have put notes on the website, and these notes were prepared by my fabulous grad student, Ariela Smovsky, who actually, she's a fantastic teacher herself. And so she gave this lecture when I taught this class 2 years ago and prepared these notes. So I was actually there watching the lecture, and I was half expecting a riot with people saying, "We want her back next time," but they took me back. Um, okay, so let me explain the data structures that go into this algorithm. So this thing very closely follows her explanation, which is a very different style from mine. So I tend to tell people the big abstract picture first, and then I give examples. She gave an example, and then at the end described the general picture. Okay, so the basic data structure is called an observation table. And the observation table is defined by two sets, S and E, both subsets of sigma star. Both S and E are finite. And it's helpful to think of S as states and E as experiments. Okay, states and experiments. So the idea is, well, I don't know what's the state structure of this machine, but as the thing reads a word, it winds up somewhere in the machine. So I'll use the word to tell me the name of a state. Okay. And how do I see what happens? How do I tell states apart? Well, if I'm in a particular state, I'll do experiments. And what's an experiment? Well, I feed in some more words and see what happens. All right. So is that picture clear? So what the table looks like is like this. Along here, the columns are indexed by the experiments. So here's a typical example. So one experiment you can do is just stay there. Or perhaps I can do this experiment, which is feed an A and see what happens. Or maybe that's my experiment. So this is just an example. Later on, I will actually do a run of the algorithm on a specific machine, which you will only discover when we finish the algorithm. Okay. And these are the states. And let me draw a double line here. Okay. So this one is not indexed by the states. It's indexed by something a bit more elaborate. It's indexed by the possible states unioned with S dot sigma. So what is this? So of course, these are not real states. These are just words, but these are your attempts to describe where you might be in the machine, which is kind of a tricky thing because you don't even know what the machine looks like. Okay. So why this? Well, S is kind of your current guess of what the states look like. And S dot sigma is, well, where do the transitions take me? So these things are actually telling you if I'm in a state S, then for each letter, I want to know which new state I go to. Okay, so Again, this is a completely intermediate uh, table. It goes without saying the alphabet I have in mind is A, B. So safe to say that there is a state corresponding to epsilon, namely the start state. And that's how you always start building these tables. And then maybe you've proposed that there's a state corresponding to where the letter B takes you. And after that, you've decided, hey, that's enough states. Now what I need to do is ask, where do I get to from each of these states? So where do I get to from epsilon if I read an A? Well, I should get to the state corresponding to A epsilon, which is just A. Where do I get to if I start in epsilon and I read a B? Well, I should get to epsilon B, which is, by the way, already there. So I don't need to create a new row for it. Where do I get to if I'm in B and I read an A? Well, I get to some state corresponding to BA. And where do I get to if I'm in the state corresponding to B and then I read a B? Well, then I should be in the state BB. Yeah, so is it clear? The things above the double line are my guesses as to where the state, what states are necessary. In this, so far, I think I need at least 2 states to describe the machine. And then these are simply telling me which states I go to as I've read the machine. Now, what do I enter in these boxes? Each box contains 1 or 0. So if we call T to be the table, so this table is just a matrix. So we'll say if there is a string S along this column, and one of the columns here is labeled with E for one of my experiments, then the entry for TSE will be 1 if SE is in the language, and 0 if SE is, oops, this is E, not epsilon, is not in the language. And how did I find out whether things are in the language or not? I asked the teacher. So you can see this is a finite table. So this is only finitely many queries. Okay. So for example, this thing being 1 means, sorry, this thing being 1 means the string BAA is in the language. Okay. And if this, for example, is 0, it means BB is not in the language. Why BB? Because it's BB concatenated with epsilon, which is of course just BB. So is the structure of the table clear? Okay. So this is the basic rule about how we fill the table. So the basic strategy is like this. You start out with an initial table, and that initial table just contains epsilon for the states and epsilon for the experiments. And you ask the teacher, what happens? Mainly you're asking the teacher, is epsilon in the language? And she will answer. And according to that, you will fill it in. And then as you propose automata, she will tell you, no, that's not right. And so you will expand the table because it means you haven't collected enough information to make an accurate guess. So what is super extremely clever is how this table was designed to guarantee to lead you to the minimal automaton and guarantee to converge correctly. Okay, so it's not like wild guesses. Hey, let me ask you these random strings and let's hope I can guess something. It's actually a very systematic way of asking which strings are in the language. So let's assume you have a DFA. Sorry, assume you have a table. with certain properties satisfied. I'll tell you in a minute what these properties are. Okay, then we can propose a DFA. By the way, part of the structure of the table is the separation between S and S dot sigma. So this double line is part of the data structure. Okay. So what we're going to do is we're going to define a machine by saying the state space is equal to, okay, let me define a few other things first. We'll define a function rho. Rho is a map from S union S dot sigma to E arrow 0, 1. That's what you expect a row to be. So for each line, you see you've got an element of S union S dot sigma, and what's contained in that row is a value 0 or 1 for each experiment. Okay, so this is exactly the type of a row. Everybody clear about this type?
Someone's asking why it's S cup S star sigma.
I'm going to tell you in a minute, damn it, wait. Jesus Christ. I told you before already, S stands for your guess as to what the states are. S dot sigma are the next states that you go to after reading a letter from sigma. Okay, that's why it's S union S dot sigma. Okay, so what does rho of S, how is it set? So rho of S for a given S in here is simply the value of the table for each E in E. Oops, each E in E. So that's how the rows are filled. So now what's the state space? So we're going to say the state space is the set of all rows. So we'll identify a row with a state. Okay, only the rows in S, not in S dot sigma. What's the initial row or the initial state? It's the row of epsilon. What are the final states? It's the set of all rows such that S is actually one of the rows corresponding to S, and T of S epsilon, which is of course T of S, is 1. And finally, the transition, the all important transition function. So it says, here I am, I'm in some state, but remember a state is just a row, and I'm reading a letter A, and then it has to be the row corresponding to SA. Okay, so I have to do this for every A in sigma. So this is why, in addition to the rows for S, I need the rows for S dot sigma. Okay, so Of course, if I just give you any old randomly filled table, I'm not going to get a well-defined automaton this way. So let me describe two extremely special properties. Or should I draw an example automaton from a table? Yeah. Anybody interested in seeing an example automaton from a table? Okay. Marianic is nodding, so I assume that means yes. So let's make a table. Oops. And let's say the experiments look like this. For some reason, she didn't fill in the epsilon column, so I will leave it out. And here are the rows of S's. So actually, this is not exactly the table. It's just a condensed form of the table. So I'll remove these things. So it's not the full set of experiments. Let's say you're looking at the possible letters in the alphabet. Those are A and B, and you're looking at the rows. And let's say you've got 3 rows. These are just the rows of S. So this one says row epsilon equals 0, 0. Row epsilon A equals 0, 1. Row epsilon B equals 0, 0. Row A equals 0, 1. Row AA equals 1, 0. So let's say after doing enough experiments, you've collected this information. So I'm just showing you how to draw an automaton. So what should come here is, of course, row AA. And what comes here is row AB. Which we're going to assume is also 0, 0. And over here, we've got row AAA, which we're going to assume is also 0, 0. Row AAB, which we're going to assume is also 0, 0. So let's say we have all this information. How will we construct an automaton? So we see that this row 0, so there are 3 states as far as we can tell. 0, 0, 0, 1, and 1, 0. We see what the start state is. It corresponds to the 0, 0 thing. I'll just write that in blue underneath. Then we see an A transition takes the 0, 0 state to the 0, 1 state. So let's call that Q2. And just to remind us, we will label it 0, 1. Where does B take us? Well, we see AB is again 0, 0. So we realize there's a self loop here. Now sorry, this should be called Q1. Okay, where does Q1 go? So Q1 corresponds to row A. And so now we have to ask, what happens when you read an A? You go to row AA, and we see that row AA corresponds to the state 10. So we need a new state, and it's going to be an accept state. So first of all, why is it going to be an accept state? Because we see that with epsilon, we get a 1 here. Okay, so from Q1, we've got, so I should label this 1, 0. So an A takes us to Q2 because it takes the 0, 1 thing to the row AA. Then we go to, where does a B take us? So we see B takes us to 0, 0. That's back here. And for Q2, we see that both A and B take us to 0, 0. Okay, so if you have all this information in the table, you can actually construct an automaton. So what properties do we need? Properties of the observation table. So what are these properties? First, an observation table is said to be closed when for all t in S, for all t in S dot sigma, there exists S in S such that rho of t equals rho of sigma, rho of S. So remember, the rows of S represent your guesses of the states. Your rows of S dot sigma represent the next state you went to. So closed means when you read a new letter, you go to a state that's already there. You don't have to start inventing new states. That's why you keep track of S and S dot sigma. So as long as you see that there are rows in S dot sigma that is not there in S, you see you don't have enough states to capture the machine. And this property is called being closed. That means when you take transitions, you stay within the states you've already discovered. Okay. So this is a crucial, if you don't have this property, then your set S cannot be representing your states because there are things in S dot sigma that are not in the set of states. So the second property you need is, supposing I've got two different rows and I read the readings on the rows and I'll say they're identical. So then I'll say, so it might be two different words there, but they lead me to the same state. But if they lead me to the same state, then when they read the next letter, they better also go to the same state, right? You can't go from one state to two different states. That would be non-determinism. So the second property is called consistency. An observation table is consistent whenever I've got two states in S and they really correspond to the same rows, and this implies that for any letter in my alphabet, Okay. So is it clear why we want this condition? Right? We're not consistently defining a DFA. If we're saying these rows correspond to states, then we find two words get you to the same state, but then after that, they take off in different directions. That can't be a proper DFA. So you absolutely need this property. So an observation table describes a DFA if and only if it is closed and consistent. So with the way the algorithm proceeds, every time you find that it's not closed, you ask for more queries. Every time you find it is not consistent, you propose new experiments. So of course, those new experiments will trigger new queries because you have to get the teacher's help to fill the extended table. And basically, every time you find, I'm closed and consistent, you propose, you construct an automaton along the lines that I just described, and you show it to the teacher. And she will give you either the thumbs up, in which case you're done, or she will tell you no and give you a counterexample. And then you use this counterexample to extend the table. You look at the counterexample and you say, oh, I didn't see this coming. So I need to have asked more questions. And so you put the new entries in the table and ask her again for the answers to these new queries. Okay, so that's the overall strategy. And you do it in such a way that as you're expanding it, every now and then you will hit a closed and consistent table, and then you propose a DFA. So the magic thing that Dana Anglo proved was this is guaranteed, guaranteed, guaranteed to work. It will always terminate. It will always produce the correct minimal automaton. And I said polynomial time. So that's polynomial in the number of states of the minimal automaton for the language, plus polynomial in the maximum size of a counterexample proposed by the teacher. So in these two variables, it is a polynomial. Okay, so now we're going to do an extended example. And this is going to be a bit like an Agatha Christie story. You won't find out the automaton until the end. The algorithm is called L star. Okay, so we're going to run L star. The L star algorithm. Okay, so we're going to take our alphabet to be AB. And let's draw our first table. So there's a lot of drawing of tables that's going to happen now. So the table always starts out looking kind of small. On this side, we've just got E. And the only experiment you start out with is epsilon, which is you're going to ask, where are you? And here we're going to put S union S dot sigma. So there's going to be 3 rows. So this row is going to be epsilon. Okay, so that's our S. We always start S is epsilon, E is epsilon. Now tell me some answers. So we're not just going to ask whether epsilon concatenated with epsilon is in the language. Let me put my epsilons in the same font. So what's S dot sigma? Well, that's A and B. So we're going to ask the teacher all these things. Is epsilon concatenated with epsilon in the language? And she says yes. Then we ask her, is A concatenated with epsilon in the language? So just a singleton A, and she says no. Then we ask, is B concatenated with epsilon in the language, i.e. is the string B in the language? And she says no. So, question for you, is this table closed?
Denali saying no.
Very good, Denali. So why is it not closed? You can
Because
turn,
there's no state. Oh, yeah, turn on your mic too.
okay, but you're absolutely right, because there's no state corresponding to zero, because remember our only state is this. So we right away see table is not closed. So then we say, okay, one of these things in S dot sigma, that should have been in S. So we add A to S and extend the table. Okay, so let's draw the extended table. Okay. So over here we've got E, and over here we've got S union S dot sigma. And over here we've got the division between S and S dot sigma. So here we've decided epsilon is a state and A takes you to a new state. And then of course we have to ask, well, where do the transitions take you? So epsilon with an A takes you to A, which is already there in our set of states. Epsilon with a B takes you to B. Our experiments are still unchanged. A with an A takes you to some state AA, and A with a B takes you to some state AB. And now we get to ask our teacher, what happened? So the teacher has already told us that this is 1 and that's 0 and that's 0. So we ask these two new ones. And she says, okay, AA is accepted, but AB is rejected. Okay. Is this table closed? Yes, because everything that you could possibly go to is already accounted for amongst the states. Is it consistent? Well, we see these two things are different. So there's nothing really to check. All right. So we get to propose an automaton. So this is closed. Closed and consistent. So we propose. So I'm just going to draw the automaton. You can convince yourself that this is the right one. So it's a two-state machine. We see that the start state has to be an accept state because we see epsilon epsilon takes you to a thing epsilon is accepted. And then there's another state, which is obviously not an accept state. So we'll call this Q0, we'll call this Q1. We see that A and B take you there. That's what we learned right away in step one. We see that B keeps you here, but A brings you back. Okay, so initially accepted. As soon as you see either an A or B, you're rejected. So you propose this, and the teacher says no. So BB is in the language, but the machine rejects BB. So if the teacher says, gives you a counterexample like that, you add BB and all its prefixes.
We just have a question from Maria who says that the above machine would reject AB, but the table accepts it? Question mark.
Table accepts it? No,
Accepts
table
AB.
table rejects AB.
Never mind. Yeah, it's okay.
Okay, so add BB and all its prefixes. So we get a table that now looks like this. So this is a thin, long table. Okay. Still, E is only epsilon. Sorry. That's E. And here is S union S dot sigma. Okay, so what's in S now? So we had epsilon as before. We had A, and now we've said add this new string that she has given as a counterexample, which should be in your language, and put all its prefixes. So what are its prefixes? Epsilon, well, epsilon's already there. P and BB. And now you, of course, also have to add all the extensions. So that means you need AA. So that's A with A added. You need AB. You need BA. You need BB, but BB is already there. BA, then you need BBA because we've added BB as a state, and we have BBB. And now we have to ask the teacher, tell us. So she fills the table for us. 1, 0, 0. So this, she just told us that's a counterexample. And so in response to our additional queries, 1, 0, 0, 0, 0. Okay. So is this closed? Yes, because what's a row? Since there's only one experiment, a row is represented by just one bit, and you see the only two possible rows are 1 and 0. It's still a and then we see everything you could go to is already here. But is it consistent?
Cole is saying that it's not consistent.
Sorry, who's saying that?
Cole.
Cole. Why is it not consistent?
Yeah, A and B both lead to 0,
Yeah,
but then AA leads to 1 and BA leads to 0.
exactly. Okay, so row A equals row B, but row AA is not equal to row BA. So when you hit an inconsistent table, then you say, I don't have enough experiments. So you add new experiments. Add A to E, because you see this one step of A showed you that the table wasn't consistent. So you need extra information precisely captured by where you spotted the inconsistency. So now we've got a new table. It's getting a little bit fatter. I think when we complete this example, it will need 3 experiments. Huh? Yeah. So here's E. So our experiments are epsilon and A. And here we've got S union S dot sigma. We've got 4 states. And these states are epsilon, A, B, BB. And then we have to put in all their extensions, unless they're already there. So AA, AB, BA, BBA, and BBB. And now we have 2 columns to fill in, so we have to ask the teacher all these queries. Some of them, of course, we already know, but for others, we don't know. So this is 1, that's 0, that's 0, that's 1, that's 0, 0, and that is 1, 0. And here we've got 1, 0, 0, 0, 0, 0, 0, 1, 0, 0. Okay. So now closed and consistent. So let's propose an automaton for this. So now you see the rows are a bit richer. It's not just 1 bit. It's actually 1, 0, 0, 1, 0, 0. 1, 0 is the same. Do we have a 0, 1? Yes, there's a 0, 1. So how many different states have we got? So it's closed and consistent, yes. How many different states have we got?
Rahul says 3. I was about to say the same thing.
Very good. Both of you are right. It is, of course, 3 states because those are precisely 1, 0, 0, 1, and 0, 0. You see nowhere do we find a 1, 1. So let's draw a 3-state machine. The fact that the start state is an accept, we knew from step one, and that fact never changes. Because no matter what new things we learn, we always remember the fact that epsilon brought us to an accept state. That means start state is an accept state. So I won't read each step of the table, but you can construct this machine yourself looking at the table. So Q0 is the start state. It's also the only accept state. A takes you there. A brings you back. B takes you here. A cycles here. Another B takes you to an accept state. Yet another B brings you here. And do I have everything? I have an AB from here. I have an AB from here. I have an AB from here. Okay. So we propose this. Teacher says, no. And she gives a counterexample. A, B, B, A, B, B is accepted by the machine, but it should be rejected. Okay, so the table is now getting a bit big for me to draw. And there are now a couple of steps you have to do. So you add, so you expand S to include ABB and all its prefixes. Okay, so some of them were already there. So now we have 6 states, or rather 6, we don't have 6 states. We have 6 rows. If you just fill it out, so there's 6 rows, and then with S dot sigma, you have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 rows in S union S dot sigma. So the table you get is not consistent. So we have to extend E. And how do we extend E? We add B to E. So now we have 13 rows and 3 columns. And if you look at the rows and columns that you obtain, you will find there are 4 distinct states. Okay. So now you can propose the machine. And the machine that you propose looks like this. So we'll call this guy Q1, call this guy Q2. So A takes you there, and B takes you here, and A brings you back from there, and B brings you back from here. And then this is Q3. B brings you here, and another B brings you back. A takes you there, and another A takes you there. Okay. So now teacher says, yes. All right. So you have learned this automaton by the systematic procedure. Okay. What does this automaton do?
Rahul is saying it's a palindrome automaton.
Palindrome. Does it accept that? No. And that's certainly a palindrome.
Doesn't it? From Q0 to Q1 to Q3 back to Q1 back to Q0.
You're claiming it accepts this language, this string? A, B, B.
Never mind, there's 3 B's. I didn't say anything. So we have Roland saying even numbers of A's and B's.
Very good. So you can see this column is keeping track of even number of A's. Here you have an odd number of A's. This row has even number of B's. That row has odd number of B's. And the start state has even number of both things. This is a nice little automaton. So just for fun, try to write a regular expression for this. Don't try too hard. So my former student, Sophia, who's now a prof in one of those US states, maybe Minnesota or something. Anyway, so she teaches automata theory, and she thought, yeah, I'll give them an assignment on regular expressions. So she gave them this automaton and said, what's the regular expression for this automaton? And then the student said, oh, we can't do this. It's very difficult. And she was going, oh God, these students. So she tried to sit down and do it. And after like several hours, she gave up. And then she found an internet website that says, type in your description of the automaton here, and we will produce the regular expression, because that's actually just an algorithm. So there's a stylized format in which you can describe the automaton. So she typed it in, and it was like a 20-line regular expression. So if any of you become instructors, never, ever, ever assign a homework problem that you've not done yourself, no matter how simple it looks. So it was a bit shocking for me, because I looked at it and said, yeah, it must be simple. And then I gave up after like an hour. A smart person would have given up after 5 minutes. So, I mean, yes, in the end, you can write it down. And I think that the website didn't produce the shortest regular expression, but it's still a huge pain to write this down. But let this be a lesson. Lots of people think, oh, regular expressions have this fabulously cool algebra. Yes, they do. But anything algorithmic you want to do, you should go through the automaton. Okay, so the handout that I've put on the course website, it should be there. Ariella Smovsky's notes on automata learning are very complete. It contains this example, including the very last picture of the table, which I didn't feel like writing because it had 13 rows and 3 columns, hence 39 entries, and was beyond the limit of what I'm willing to write down on my iPad. But she systematically goes through this example, and then she gives the algorithm, which is basically what we did. So you start by initializing the observation table with S set to epsilon and E set to epsilon. You ask the teacher, is epsilon in the language? And she will answer. You also then have to ask it about S dot sigma, so all the one letter extensions. And then you go from there. As long as this table is not closed or consistent, if it is not closed, find an S and an A such that the required rows are not in S dot sigma, are not already in S, and add them to S. And if it's not consistent, then you have to add new experiments. Okay, so every time it's a failure of closure, you have to extend what the states were. Every time it's a failure of consistency, it means your observations are not refined enough. So you have to add new observations. And if you do this systematically, extending it, you will converge to the minimal DFA that recognizes the language. So essentially, a similar algorithm works for weighted automata. So I have a young friend called Alexandra Silva. I've mentioned her name several times before. And at some point, I was having a drink with her in a bar or something, and I said, you know, this L star algorithm of Dana Angluin's, there should be an abstract presentation in terms of category theory. And it turns out shortly after that was my 60th birthday, and they celebrated my birthday by publishing a book about whatever they felt like writing. Anyway, so what she contributed to this book was an article about how to present L star in an abstract category theoretic way. So instead of talking about sets and S and E being sets, there were morphisms in a suitable category. And it was just rewriting L star in this abstract language. But then she noticed, okay, if I've written it in this abstract language, it doesn't have to be done with sets. It can be done with vector spaces. And she found that exactly that algorithm, if you look at it for automata on vector spaces, that's exactly weighted automata. You get the weighted automaton learning algorithm. And that led her to, well, if that's the case, let me try it in yet other places. And she just started spouting out new learning algorithms by just instantiating this categorical presentation in different settings. So now she has a huge European Union funded project called Categorical Automata Learning Framework, CAF for short. So, so that shows you at least one virtue of doing it in an abstract way. If you want to read more, including the proof that this converges, which is not very difficult at all, there is the original paper by Dana Angluin is absolutely the best. Nobody has written a better presentation than what she wrote to me originally. And in her paper, she also explores what happens if you have probabilistic automata and convergence rates and things like that. So this is kind of automata theory meets machine learning to some extent. So another place where my students are working on this is trying to understand what an RNN does. So you take, so what happens with neural networks, especially deep neural networks, is that you have this neural network and you go through this complex training process involving gradient descent and all, and in the end it learns something, and then it does stuff, but then you ask it, it makes decisions. So unfortunately, these neural nets are used to make decisions like which areas of the city should be more heavily policed and who should get mortgages and stuff. And mysteriously, it seems to think that the black areas should be more heavily policed, and people with names like Smith should get the mortgages, and not people with names like Rahul Kumar. So, so there are lots of questions like, wait, we can't just train a neural network and ask it to make decisions for us. We should try to understand what it's doing. And then, the people who implement neural networks say, well, we ran the training process and it set all these parameters, hundreds of thousands of them all got set. And based on these parameters, it's making these decisions and we don't understand how it decided. So there is this whole question about interpreting what an RNN does once it has been trained. Okay. So this whole thing of saying, I don't know what it's doing, we just trained it and that's what it decided, is a bit of a cop-out. So it's now a very important aspect of machine learning and AI in general to not just say, yeah, I have a powerful training method. You also want what's called explainable AI. Once you have trained it, you should be able to explain what it is doing. So one approach is to say, okay, if it's making decisions, maybe yes, no decisions, what are we feeding it? We're feeding it strings of data. So in some sense, it's working as an automaton. So maybe if we had a picture of saying, well, what it got trained to do was behave like this automaton. And hopefully the automaton is much simpler and you can look at it and try and understand what is this automaton doing. So one idea, use RNN as the teacher. And extract a DFA as the explanation of what the RNN is doing. So this idea has been published and explored experimentally by Israeli scientist Gail Weiss. And it's now being explored by me and my fabulous graduate student. All my graduate students are fabulous. Alika Utepova. So this is one thing you can try to do with this automata learning algorithm, of course, extended to the probabilistic world. Okay, it's 11:51. Let's take a 20-minute break. We'll come back at 12:10, and then we'll have a short meeting after that. Okay, and I will answer questions while we are waiting. So let me stop share. And let me recording. And then I do share screen. Share. Screen mirroring. Zoom. Oops, what happened? Okay. So During the break, Maria was asking me about questions 6 and 7, which basically is based on material I haven't yet explained to you. I'm going to explain it now. So this is adding, adding fixed point operators to linear temporal logic. Okay. So I have to explain to you what are these things called fixed point operators. If you look at box phi, one way of writing box phi is to say, well, phi is true now, and in the next state, also phi is true, and in the next state after that, phi is true, and so on. Right? So that's a nice way of explaining what box phi means. And you look at that and you say, oh, well, I don't really need box because I can express it in terms of circle. The only thing is this formula has infinitely many conjunctions. So it's not how we normally think of logical formulas. But it turns out that in some cases, there's a finite kind of way of expressing things like this. So we've all learned basically how to cope with certain infinite things in a finite way, right? If I give you an a universally quantified formula about something about the integers, you don't go and say, well, let me prove it for 1 and then for 2 and for 3. What do? You use induction. So something like that should be possible. And in fact, fixed point logic is kind of a way of incorporating an inductive definition into the logic. So here's how it works. First, syntax. And remember, syntax is just notation. It tells you what's the correct notation without explaining anything. The syntax may be suggestive, but by itself, it's not a formal explanation of anything. So the formulas in the syntax are atomic propositions. So there's some set of atomic propositions. Then I'll allow you Boolean combinations. So phi 1 and phi 2, not phi. And now I want to define temporal operators. So I'm going to allow you circle phi, which as we know means in the next state, phi is true. But now I'm going to introduce 2 new gadgets, and they're written like this. And there are 2 things I need to explain. First, what is this capital X thing? Because it's not one of the propositions. And then what are these Greek letters rearing their ugly heads in here for? Mu and nu. Okay, so X is a new syntactic entity. It is a variable that can range over formulas. Okay. Mu x and nu x are variable binders. In the same sense that we introduced the notion of binding in 302 or bound variables associated with quantifiers in ordinary predicate calculus. So these are bound variables. If I leave the x floating around, then the formula cannot be interpreted without additional structure. Okay. All right, so let me write down examples of things that we can write down in this logic. So I can write down mu x phi and circle x, or mu x phi and circle x. So this is bound. And nothing stops me from introducing x, capital Y, capital Z, and having three of these things. So mu and nu are called fixed point operators. How are we going to interpret them? We're going to use fixed point theory on lattices, which is why I have postponed telling you about it till now. Okay, so we know, what do we remember from fixed point theory on lattices? Recall every monotone function from a complete lattice to itself has a least fixed point and a greatest fixed point. Okay, so we're going to exploit this fact to ensure the meaning of our mu and nu. So mu is going to stand for least fixed point. Nu is going to stand for greatest fixed point. So remember, we said monotone functions have fixed points. So we need to ensure that when we're trying to construct construct functions and interpret them through fixed point theory, we need to guarantee that they're monotone. So we are not allowed to put a fixed point operator binding an x unless x appears in the scope of an even number of negations. So mu x phi and not x is not allowed. Okay. Mu x, x implies phi, is not allowed because x implies phi is the same as not x or phi. Okay, so you have to watch out for those implications as well. If you're on the left-hand side of an implication, you are negated. Okay, so I'm going to allow negations as long as there's an even number of them, because every time you put a negation, it flips it from making it monotone to making it anti-monotone. So if I put 2 negations, you're back to being monotone. 3 negations, anti-monotone. 4 negations, back to being monotone. So just count the number of negations and be careful to count also left-hand sides of implications as negations. Okay, so this is a purely syntactic restriction that you can check. So if it doesn't have that syntactic monotonicity property, it's a rejected formula. It's not a valid formula. Okay, so given this restriction, we now know, so we're now ready to interpret these 6-point operators. So recall, we defined the semantics in terms of sequences. So we had a sequence sigma and a formula phi. We gave conditions for when does sigma model phi. So given that, we will say a formula phi in square brackets denotes a set of all the sequences that model phi. So this thing defines a set. This is called a definable set. Not all sets can be described like this. There are some sets that are exactly the set of sequences that satisfy a particular formula. Okay, so given a formula with a free variable, we interpret it not as a set. So one way of describing the semantics of formulas is to describe these sets instead of describing what it does on individual sequences. That's just an equivalent description. We interpret it not as a set, but as a function from sets to sets. So the interpretation of a formula that contains one of these embedded variables, so it's not a set of things that satisfy X, because that doesn't make any, that satisfy phi, because my formula might say, you know, psi and X, and I'll say, well, what the heck is X stand for? So the way I interpret it is, if you give me an interpretation for X, then I'll give you an interpretation for phi of X. Maybe I need square. So here, this notation means interpret or substitute the set S regarded as a formula for X in phi. So supposing my phi of X was something like this. It has psi and circle X. So how is this interpreted as a set? So if I take this formula and apply it to some set S of sequences, and the set of sequences that satisfy this formula are all the sigmas such that sigma satisfies psi and sigma 1 dot dot is in S. Why sigma 1 dot dot? Because there's a circle there. Okay. So in this way, any formula with a single free variable can just be interpreted as a map from sets of sequences to sets of sequences. Is this part clear? So fact, with the restriction these functions are always monotone. And the power set of sigma infinity or sigma omega, which we're using to interpret this, is a complete lattice. Okay. Good. So now we define to be least fixed point of this function phi of X. So formulas with a free variable are interpreted as functions. Formulas with bound variables are interpreted as sets. So even though phi of X was a free variable and was interpreted as a function, mu x phi of X does not have free variables because mu is a binder. So this free variable X there has now gotten bound. And this is now interpreted as a set. And which set is it? It is the set that is the least fixed point of this function phi of X. And analogously, this is greatest fixed point of phi of X. Okay, so maybe we should look at a couple of examples. So we'll call this mu LTL. So it just has Booleans, just has circle, and it has mu and nu. Interpreting what happens when you've got nested fixed points is a nightmare. So, I mean, it has a well-defined meaning, but to intuitively read what it means to have mu x, mu y, mu z, all stacked one inside the other, I think by level 3, it's unreadable. So don't go wild with trying to interpret formulas like that. even experts can't interpret them in human terms. Okay, we can just think of them in formal terms. But some very basic formulas can be interpreted just with fixed points. So let's do box. Box phi is nu x, phi, and circle x. How do you calculate the greatest fixed point? Well, you start from the top, you apply the fixed point operator, and you keep intersecting. How do you interpret least fixed points? You start from the bottom, and you keep building up and taking union. So let's look at approximations to this. So at the first step, we say, we don't know what x is, it's just true. So we'll say, so our first approximation, we'll call it box phi 0. We just say it's true. And every sequence satisfies this. Then we'll say, okay, let's use this interpretation to get a more refined one. Box phi sub 1. So these are all approximations. We'll say, okay, so we look at this and we say it's phi, and in the next step, box true must hold, but that always holds, right? So this is just the same as phi. So phi has to hold now. In the next step, we don't care because, it's just always of a trivial proposition, and the trivial proposition always holds. Then we'll say, okay, let's refine our understanding. So these things are more and more refined understandings converging to the fixed point. So we'll say, okay, first we know that phi must be true, and then we know in the next step, box phi 1 must be true. That's how we get to box phi 2. Well, box phi 1 says phi. So we say, this has to satisfy phi and circle phi. Then we'll say, okay, we've got now a better understanding of what box phi means. Let's try and refine it further. So we'll say, what is this? Well, it's phi. And in the next step, box phi 2 must hold. But box phi 2 is phi and this. So that's circle of phi and circle phi, which is phi and circle phi and circle phi. And now by a mysterious process called undergraduate induction, we conclude that box phi n is phi and circle phi and circle phi and up to n circles. And then we intersect all of them. So you see now that what we thought of before as an infinite formula, we actually see that it's a fixed point formula. And this is a very finite looking formula. Very finite looking formula. Okay, so you can see that this is kind of what box is supposed to be. So you can see that this thing gives us correctly box phi. Okay, so the formal semantics is there to make this rigorous, but intuitively you can think of, how did I get to the greatest fixed point? I start from everything is true, and then I refine that and intersect them all. So you see the opposite of induction. Induction says start from the bottom, build things up, and take the union. Starting from the top, cutting things down and taking the intersection is called co-induction. So greatest fixed points go with co-induction, least fixed points go with induction. So let's see how we can define diamond. So we'll say diamond phi is least fixed point of phi or circle x. And I will leave it after this as an exercise for you to do until, which is only slightly more complicated. But box and diamond are good enough for the intuitions. Okay, so We proceed in the same way. We iterate as above, but we start from the bottom. And build up, taking unions in the end. And this is more or less how you think of induction. So there's a very nice duality between box and diamond and between mu and nu. And it was an open question for a long time, whether if you keep stacking more and more news, do you get more and more expressive power? Or is after some stage, does it saturate? And Julian Bradfield proved in his PhD thesis that this is true, that you always get more expressive power. So this was a sensational result, especially given he was just a PhD student and he immediately got a faculty job as when he graduated. Okay. So let's try and understand this diamond thing. Okay, we start from the bottom. So we say our first guess at what this thing means is simply false. And the set of sequences that satisfy this is the empty set. Then we say, no, wait a minute. Box phi 1, let's look at the structure. We'll substitute always our last piece of understanding for X and see if we can refine it. So we'll say, okay, look, either phi is true or in the next step, something impossible happens. So that is garbage. So it's basically phi. Yeah. Then we say, okay, we've got a better understanding now. Let's see if we can refine it further. So we'll say, next step, we see, oh, phi is true, or in the next step, diamond phi 1 is true, but diamond phi 1 is phi. So it's either phi or in the next step phi. Diamond phi 3. Similarly, it's phi, or in the next step, diamond phi 2, which is phi or diamond phi or diamond, not diamond, sorry, circle phi or circle phi. And then this goes on. And now the limit is obtained by taking the union of all these things. So at least intuitively, though not formally, diamond phi is phi or circle phi or circle phi or ad infinitum. But of course, that's not a real formula because that's an infinitary thing. But this, you see, is a finitary way of capturing what looks like an infinite formula. So you can do box, you can do diamond right away. Maybe it's interesting to see what happened if I use the wrong fixed point operator. So let's try. We will use a new modal operator. We will call it heart. Okay, so heart phi is mu of x phi and circle x. So it looks like box. Looks like box, but instead of mu, I have got nu. Sorry, instead of nu, I've got mu. Okay, so box has the nu and heart has the mu. So let's see. I mean, this is something, this is a formula, it's syntactically valid and all. What does it stand for? So we'll use the same approach. We'll start from the bottom and build it up. Why start from the bottom and build it up? That's what mu tells us to do. Okay, so first approximation to heart phi is false. Always we start from the bottom. That's what it means. The set of sequences satisfying false, empty set. That is the least element in our lattice. Next step. I'm not very good at making these hearts. Heart phi 1 says we substitute in there. So it's phi and circle false. Circle false is phi and false. What's the truth value of phi and false? Truth tables. Anybody on the chat, Marianic? You're the co-host.
Yeah, F.
Very good. If you've got a conjunction and you know one of them is false, there's no point waiting for the other one. Right? Hey, fixed point. So we are already at the fixed point. So heart phi is simply equivalent to false. Not a very, probably not what you had in mind. Let's try another modal operator, again using the wrong fixed point. So we will call this spade phi. And this is defined to be, so remember, we defined diamond with a least fixed point operator. So now we're going to say greatest fixed point x, phi or circle x. Okay, so first approximation, sorry, 0th approximation is true. Every sequence satisfies this. Greatest fixed point, so we start from the top and go downwards. Least fixed point, you start from the bottom and go upwards. We refine this and say, okay, we use spade sub 0 in this and refine it to get spade sub 1. So this says that's phi or circle true. Circle true means in the next state, anything can happen. So how many sequences satisfy that? All of them. Remember, these are infinite sequences, so there's always some next state. And basically, we're not checking anything in the next state. We're just saying, if you have a next state, you're in. So this is simply phi or true. Can anyone simplify that for me?
Well, Adam, Maria, and Melinda are saying true.
Yes. Well done, Adam, Maria, and Melinda. When you have an OR and you found out that one branch is true, no need to wait for the other branch. Yeah, it's already true. So we are at a fixed point already. In short, what does it mean precisely to be at a fixed point? Spade true is nothing but true. So true is a fixed point. Applying spade to it doesn't change it. So spade of phi is just true, not very useful. Okay, so just because I said the way you understand these fixed points is through an iteration. It doesn't always have to be an infinite iteration. Sometimes the iteration stops in finitely many steps. Here stops immediately. Okay, so your assignment, should you choose to accept it, is use these fixed point operators to define odd p. Remember, we talked about odd p when we introduced temporal logic. We said, hey, odd p, easy to write down a regular expression for it, but we can't seem to be able to define it in temporal logic. So of course, the hard part is to show you can't define it in ordinary temporal logic. It's actually like a two-line, almost cheap question to do it with the fixed point operators. Okay. So proving that it's not definable would be quite a tricky question indeed, but I've kind of told you what to do. I've kind of led you through how the proof works. So there's a whole calculus called the mu calculus, which is basically modal logic plus fixed point operators. And some of the fundamental results in this field were obtained by Dexter-Cozen. And later on by Dexter-Cozen and Rohit Parikh. Okay, so I will stop here. We are halfway through, yay. Any questions? I will turn off the sharing. Turn off the sharing. And I will send this to my ah. Okay. Okay, good. So it has been sent. I have I stopped recording?